were to be applied to real world situations. Okay, what do word problems have that regular problems don't, typically speaking? When you have, besides words, besides the obvious, what do word problems tend to have that regular problems don't? No, regular problems have numbers too. Nobody? No? Nobody wants to take a guess? Units. Word problems have units. They're not just numbers. They usually have measurements. You're measuring something. People. You're measuring volume or weight or length. Or, there's some type of a unit involved. So if you have a word problem that says that some amount is changing exponentially, we can apply what we know about growths and decays to a real world model. This is the real world model of a growth and decay. So I'd like to compare this. This is where I would tell you to write this in. I would like you to compare this to what we already knew about exponential growths and decays. So let's compare and contrast. What used to be our output, which is the f of x, the y, what does that become in a real world model of an exponential function? If you can understand my handwriting. You can. The final amount. Yeah, whatever it is that you're counting, the measurement, it's after you've undergone this exponential change. So like, let's say, Decay Fisher enters the 9th grade as, what are you, like maybe 5'9", 5'10"? No, 5'6", you feel taller. So, all right, he is 5'6", but his height grows exponentially, not linearly, but exponentially until, and it grows exponentially by a rate of 50%. No, that's too much. 10% annually. How tall will he be by the time he's a senior? Like that's when something changes basically by multiplication. Instead of by adding, you're multiplying. You'll learn about that more next week when we do geometric sequences. So if I get his height and each year I multiply by a number, then that original number, which is his height in this case, is changing exponentially. So whatever that number is going to end up being after some type of time has passed, that's the output. Okay. What used to be the A, which is the what was the vertical stretch, the flip or whatever. Now that's going to be represented by an initial amount. That's what you start with before time passes. What used to be the base is now called the growth factor. The growth factor is going to be the number 1, that's not an L, that's a 1, pardon my handwriting, plus some type of rate of change. Now, I know this is a little bit messy here, but what I mean by this, what does rate mean? What does rate sound like? Rate, what other word does rate sound like? Seriously? Huh? Oh. Had beans for lunch. What does rate sound like? No? You say, oh, Mr. Romero, rate sounds like ratio. And then I'm like, oh, yeah, that's good. It does sound like ratio. Hey, and what's a ratio? And then you would say, a ratio is a fraction. And I'm like, wow, that's great. You guys are doing awesome. And then what else can fractions be written as? Yeah. As decimals are really, and what they're going to be expressed as in the word problems are usually as percents. Remember, like when I was talking about Decay's height, and I just threw out a number, I'm like, oh, it's going to grow by 10%. These rates are normally in word problems expressed as percents, but when you plug them into a formula here for R, yeah, you have to make them into a decimal. So what happens is, if we're going to have a growth, well, you'd have to have a positive. The rate would have to be greater than 0 because we learned back when we learned growth and decays, what's true about the base of a growth. It's larger than 1. So if we're going to start with 1, if every growth factor starts with 1 as the base, but then you want to have a growth, you have to be bigger, so you have to add a positive. Whereas if your amount is going to decay, your rate of change would be less than 1. I'm sorry, not less than 1. Sorry, be less than 0, be negative. And then when you add a negative, that's what makes the growth factor become less than 1. And you take this to the power of the amount of time that's passed. So when you compare and contrast, what else does that tell you? That we don't need to deal with any type of translation. There's no horizontal shifts or vertical ones either. Okay, so Reed gave me the stink eye. That means she's confused. So let's see if we can unconfuse her. What they've done right here on this worksheet is giving me the exact same formula, and then they explain it using their words. I use my words. They're very similar. And we see rate of change, we see time, we see initial amount, we see final amount. So let's just do examples until we can't do examples anymore. Example 1, the population of Johnson City. So here, what are we measuring? What does population measure? People. It measures people. Of Johnson City in 2005 was $25,000. 25,000 people. The population was 25,000. Since then, the population has grown at an average rate of 3.2% each year. So write an equation to represent the population of Johnson City in 2005. If you just want to use y equals, that's fine. If you want to be fancy and use function notation and even use like letters to help you remember, what are we measuring here? Population. And what is population going to depend on? And year is a type of? Time. Good. So population depending on time is equal to. What comes first after the equal sign on the real world model? The initial amount. At the beginning of this time period that we are measuring, what is the initial amount of people? 25,000. Times my growth factor. Growth factor is going to be, and I'm not even going to use the dot. Let's just use the parentheses. Okay, 1 plus or minus, depending if it's a growth or a decay. Is this population growing or decaying? It is growing, so it's going to be plus the rate of change. What's the rate of change here? It's 3.2%, but we're not going to put it in as a percent. We're going to put it in as a decimal. So you have to know how to convert a percent to a decimal. You have two options. If you have become surgically attached to your calculator and you cannot breathe without it, you can just get 3.2 and divide by 100. You can get any percent divided by 100, and your calculator will tell you what the decimal equivalent is. Or you can just get the decimal and move it over 2 spaces. So in this case, I'm getting 0.032. Okay, to the power of time. All I want to be able to write is the equation. Now, can I simplify any of those operations? Are there any operations there that I can do? Yeah, the addition. You can always do the addition. So here, my population based on time is going to be 25,000 I wrote that wrong. Sorry, I forgot the zeros. 25,000. I put 2,500. 25,000 times 1.032 to the power of t. That's just the equation. So according to this equation, what will the population of Johnson City be in 2015? So now we're going to get this and use it for substitution. Sorry if I misled you by the underlining of 2015, but the thing is, this is the equation, but now I'm going to use the equation. I'm going to substitute into it. What am I going to plug in? Well, yeah, I'm not going to plug in 2015. We want to know how much time has passed. So from the time we started measuring in 2005 to 2015, how many years have passed? 10 years. So I'm going to put P at 10. I'm going to evaluate the function at 10. So the population after 10 years is equal to 25,000 times 1.032 to the power of 10. Normally I'm big on steps and showing one step at a time and all that stuff, but there's so much usage of decimals in these types of problems that I would just advise you to put the whole thing in the calculator at once. So especially if you have a fancy smancy calculator that has a little blinker, you can just type it in as you see it. You put in 25,000 times 1.032 power of 10. The calculator should know order of operations, so it should know to take 1.032 to the 10th power first, and then multiply times 25,000. But if you don't feel comfortable that your calculator knows how to do that, you can take 1.032 to the 10th power first, like if see. I used to have one of those single line calculators out there. Most of you guys have these. Like if you have these that have the blinker on it, you should be able to just type it as you see it. But if not, take 1.032 to the power of 10 first, and then times 25,000. This doesn't tell me where to round. But what are we measuring? People. Can you have a partial person? Nah. So since you can't have a partial person with people, you should actually always round down. Because even if I had like 0.97 of a person, that's still not a full person. So I'm getting the population after 10 years should be around 34,256. Let's skip the next two because those are just population ones. And if one of these was a decay, I do it. But I just want to try to get the most out of this. So you can do those later on your own. If I'm available in the mornings for help. On those 2 review days, if you run out of problems, I can always come back and do these. Hopefully you're bringing your notes with you to class each day. So I'm just going to kind of jump around these things. Here, look, here's decay. Perfect. Let's do this first one, depreciation. Notice how the formula here, the way that they write it is the same. The only difference is the rate is going to be negative on a decay. So the original price of a tractor is $45,000. The value of the tractor decreases at a steady rate of 12% per year. So let's write an equation. What are we measuring now? Price, yeah, you can call it V for value if you want. Yeah, that's good. Just so that you don't think it's always a P. Let's call it a V, value. What is the value of the tractor going to depend on? Time again. In this case, we're measuring value in dollars, but what are we measuring time in? Years. What did I tell you was the main difference between word problems and regular problems? Units, yeah. So those are the units here. There's two units. There's dollars and time. Time is being measured in years. So after the equal sign, what's supposed to come first in an exponential model? The initial amount, which is 45,000. Times. So always start with a 1. But now, since this is a decay, I'm going to subtract. How would I write 12%? 0.12 minus 0.12 to the power of the amount of time that passes. This can be simplified. You should always simplify if you can. 45,000 times 0.88 to the power of time. And that's just the equation. But now comes substitution. What is the value of the tractor in 5 years? What am I going to plug in for time? Yeah, now since time is in years, last time I had to subtract because they were giving me the actual number of the year. I had to figure out how many years had elapsed. But now they're telling me that there's 5. So you should know from function notation last term. You put the 5 there, and then 45,000 times 0.88 to the power of 5. Use your trusty calculator to type it in all at once. Or if you want to go one at a time, take 0.88 to the 5th power first, and then hit times 45,000. I'm getting that after 5 years, the tractor will be worth, well, now this is money, so they don't tell me where to round, but what should I round to? If it's money. The hundreds place, yeah. And with money, you should actually all, well, typically they try to round up. Here you're rounding up anyways. I'm getting 23,747 and 94 cents. So it looks like in 5 years it's pretty much lost almost half its value. Keep that in mind when you buy your first tractor. Alright, this is a nice one to do because this is population again. But it looks like nobody wants to live in Bulgaria because in Bulgaria the population has been decreasing by an annual rate of 0.89%. If the population of Bulgaria was about 7,450,349 in the year 2005, predict what's the population going to be in 2015. Old problems, huh? Here, this is not broken down into pieces, so we're going to do this all at once. Let's do population. What is population going to depend on here? Time. So what's the initial, when we're starting to count, what's the population of Bulgaria? 7,450,349. Parentheses, we start off with a 1. Is this a growth or a decay? It is a decay, so it's minus 0.89, 0.89, 0.89, 0.0089, because it's 0.89%. Anytime you want to get rid of a percent sign, you have to move the decimal, even if it feels funky. You're going to be tempted to just put 0.89. But you're still converting a percent to a decimal, so you gotta throw those extra zeros in. Oh no! And then that's gonna be to the power of time. So 7450349. 0.9911. 911. Is that correct? Can somebody check my math for me? We did it first. How many years passed by from 2005 to 2015? 10. So let's evaluate this population function at 10 years. 7, 4, 5, 0, 3, 4, 9 times 0.9911 to the 10th power. Caleb, would you ever want to live in Bulgaria? What other country would you want to live in if you could? It's really expensive there. So I'm getting that, remember, we're measuring people again, so let's go to the nearest whole number. I can't round up with people because you can't have a partial person unless they're really short. So 6,813,203. Got something different? You got the same thing, Jay? Let's see, we already did a depreciation problem, and I told you we're gonna skip half-life. Here's another card depreciation, so let's just keep on skipping through and see if we can find. Here we go, bacteria. Everybody loves bacteria, so let's do a bacteria problem. A dish has 212 bacteria in it. The population of bacteria will grow by 80% every 2 days. How many bacteria will be present in 15 days? A little bit of a tricky one. What are we measuring? Population of bacteria. I'll choose a P. What is that going to depend on? Also time, but now we're measuring time in a different unit. Well, it's being measured in days, yeah, instead of years. What's the initial amount? Yes, 212 times the growth factor starts at 1 because it's a growth we're going to add. What is 80% as a decimal? 0.8. We'll leave it at time for now, but this is where it's going to get interesting. I'll go ahead and simplify. That's the first phase. Now I have my equation, and I'm able to plug in whatever I want, right? But now when it goes to time, does anybody have an idea what you're going to plug in? If they want to know what's going to happen in 15 days? And if you can understand, this is actually going to help you when we do compound interest next week. If you can understand this concept, what I'm about to show you, this is the exact thing that we're going to do when we do compound interest. We want to know what's going to happen after 15 days. Remember, the growth cycle, if you will, okay, in order for this to grow by 80%, how long does it take for it to grow 80%? 2 days. So like one cycle is 2 days, and then another cycle 2 days, and 2 days. So we're not asking you how many days are in 15 days. We're asking you how many double days are there in 15 days. And if you're ever not sure, what you would do is divide. So we would say P at 15 over 2, because it's 15 total days divided by how long it takes to get through a cycle, is equal to 212 times 1.8 to the power of 15 over 2. Some of you were saying 7.5. That's exactly what 15 divided by 2 is. Do you understand how to get 7.5? Be my guess. Put 7.5. So we get 1.8 to the power of 7.5, and that times 212. So now the population of the bacteria, that's why they say one day that's going to take over the world, the organisms. The population at after 7.5 cycles, it's gonna be and it doesn't tell me where around. I guess let's assume you can't have partial bacteria either. So let's just say 17, 4, 13 is what I'm getting. If you got something different, let me know. This is as much of a calculator lesson as it is anything else. Making sure you know how to plug these into your calculator. Everybody got the notes, right? I'm not throwing the extras. You want to try to do number 2 by yourself? Mealworms. Tell me how many mealworms will the class have for their experiment in 5 months? Caleb, you finished? Are you thinking about mealworms? Those are worms that you can eat for every meal. And you got it? What'd you get? That's what I got too. And land, is that what you got? You're just ahead of everybody? Are you ahead of everybody? So in June, a 5th grade class start, so let's see, we're measuring here, I guess, let's just use an M this time for mealworms, even though I guess it's population. Yeah, it is population. Let's do population. They use the word population. What does population depend on? Time again, but what are we measuring time in months? Okay. The initial amount is 10. The growth factor, actually here they tell you what the growth factor is. They tell you it's going to double. But if you want to just put 2 there, you could. But if you want to know how they got the 2, we always start with 1. The population is growing by 100%. What's 100% as a decimal? 1. 1 plus 1 is 2. So the population of the mealworms is 10 to the power of 2. Sorry, 10 times 2 to the power of time. And how much? Here we're measuring time in months, and the cycle is every month. Every month we get a new cycle of worms. So how many months pass by in 5 months? How many months do we have in 5 months? 5, yeah, it's just 5. So the population after 5 months is going to equal 10 times 2 to the 5th. Plug that into your calculator. And your calculator will tell you 320. And I guess I've been doing a bad job of that. You know what? I probably should be putting like units, because I have a feeling that when they give you a key, they're going to force me for you to put. So like that was bacteria. This was mealworms. On the one that before that we did with money, you should probably go put a $sign on it. On people, you would just put people. Or Caleb's. How many Caleb's you have? We did population already. So let's see, school age, right? Here we go. Let's do number 4. You do number 4, I'll do number 4, and then we'll see if we have the same answer. You got it, Caleb? You thinking about basketball? About Tobias Harris? Imagine if you had Tobias Harris to walk you to class. That would be fun. Nobody? Jada, you got it? Shobi? President Shobi? Vice President Ingrid? No, too hard. Marquise? King Marquise the Third? Just that. That's what we're here for. We're here to check and see if you got it. That's not what I got. That's what I got. Yeah. Is that what you got, Brandon? No? All right, so let's see what we got there. Over the last several years, tell me about it, there's been an increase in the amount of school-age children carrying cell phones. Current estimates, currents. So right now, that's the initial amount. So let's see, we're measuring, let's do S for students, even though my S's look like 5s. And what are the amount of students with cell phones depend on? With time, and you can see time is always a very common input in word problems. That's going to equal the initial amount, which is 1237, 3 zeros, times. See, instead of here doing 1 plus anything, they actually just give you the growth factor. What's the growth factor here? A little sneaky. Huh? Yeah, it triples. It's the 3. Triples. So the growth factor is already 3. So the power of, well, see, it triples not every year, it triples every 10 years. So what we want to know is how many times does 10 years fit into 25 years? So for now, I'll just put time, but once I plug it in, 25 divided by 10 is 2.5. There's 2.5 cycles that we're going to be measuring. So times 3 is 2.5, and you can knock that in all at once in your calculator. And we get that the amount of students in 25 years with a cell phone is going to be 19,829,000. Wait, no, sorry, I wrote that wrong. 19,282,921. Facts. Okay, number 5, we already did population, so it's not that I don't want to do it, I'm just trying to give you some variety. Ooh, catfish. And weight, the weight of a catfish. All right, let's do number 6. Do you like cell phones? Do you ever Google pictures of catfish? They have like the whiskers. Go, Ingrid, go. Go, Ingrid, go. Let's go, Marmy, let's go. Hoo, hoo. You got it, Decay? Brandon, you got something? 3 million? That's gonna be a big catfish, man. You're gonna be eating for a while. I mean, that's another nice thing about word problems that it offers some context. You were doing the population thing? Okay. No, catfish. He's a little catfish. And you eat for like the rest of your life for that catfish. You tired, Nakai? Want to the game tonight? Study. Martha? Got it? No. Marquise? No. I know Anne has it. Anne always has it. Does anybody other than Anne have a Kiara? Haven't heard from you today. Let's do it together because we're running out of time here. So here we're going for weight, I guess. So W of a catfish, what does it depend on? Time, yeah, time's a very common input. It's equal to, what does a catfish weigh at the beginning? 0.06. 0.06 times. They tell you it's a growth and it's increasing by 10%. What is 10% as a decimal? 0.1, so we go 1 plus 0.1 to the power of how many days? Or actually, well, not yet. I'm sorry. Right now it's just time. 0.06, 1.1 to the power of time. So now is when we plug in 40 days. And how many days are there in 40 days? Yeah, 40. That's why I put a 40 there. 0.06 times 1.1 to the 40th power. When you put that on your calculator at the same time, it doesn't tell us where to round, but since they went to the nearest hundreds, I'll do them the same favor. I'll run the nearest hundreds. I am getting approximately 2.72. And if we were to put a unit, this was in grams, so it would be 2.72 grams. And is that what you got? Good. Population, boring. Bacteria, we did. Investment, boring. Population, are depreciating, we did already. Keep on going. Okay, let's do termites. Go to the page where we have termites. The house down the street has termites in the porch. The exterminator estimated that there are about 800,000 termites eating at the porch. He said that the treatment he put in on the wood would kill 40% of the termites every day. How many termites will be eating the porch in 10 days? Okay. You do it, I do it, we do it. let's also assume that you can't have partial termites. So send me home here on a good note by somebody other than Anne telling me how many termites are there after 10 days. Why you? Well, it depends on what the decimal is, but why would you be dividing? Yeah. No, he gave up. No, do it. Come on. That's not what I'm getting. I might be doing it wrong. And am I doing it wrong? Is he right? No, I didn't. Yeah, that's what I got. So let's see. Here we're doing termites. So let's do termites. Depends. Oh, no, I don't want to do two. Let's do population then. Population of termites depends on time. Equals how many termites were there at the beginning? I'm wondering, do you guys think it's like a calculator issue that you guys just don't know how to put into the calculator? Or is it you don't know how to write the, like, when you see that I'm writing the equation the correct way, is that different than what you had on the paper? Or is it just that we don't know how to key it in the calculator? Or you don't have all that stuff. That's also true. I think it is like 800,000 times. We start with 1. When you get treated for termites, are you adding termites or killing termites? Yeah, you're killing them. So 40% is 0.4 to the power of time. So termites is 800,000 times 0.6 to the amount of time. How many days are going to pass by in 10 days? 10. So if you take 800,000 times 0.6 to the 10th, that gives you, this will be on the video, around 4,837. We'll continue on this tomorrow.